Hi, and welcome to this video on integration by substitution for calculus. This will be the first video in probably a three-part series here on all the different things that we can do with U-substitution, including some integrals later on that will have bounds, because that will take us a few more steps than these indefinite integrals that we are going to start with. So let's see how we do this. Now, it is important to note that we still really only have trigonometric integrals that we know how to do, basic power rule, and we also have under our belt maybe the antiderivative of 1 over x being natural log of x, some of our basic differentiation rules turned into then integration. We do not have product, we do not have quotient, or anything like that. This U-substitution is going to basically help us undo the chain rule. So when I look at this problem, I understand that many of you might see a product, but what I see is perhaps something that is there because I required chain rule to find the derivative. Remember, when we find an antiderivative, we're basically saying that this was the derivative when I took the derivative with respect to x, and I need to work backwards and figure out what that original function looked like. So perhaps that times 2x was there because of a chain rule type thing. So what I want to do first is really just look at this, and I promise I'll delete it here in a second, but I want to look at this as a whole bunch of stuff cubed, because that's where I can see my composite function idea. That's where I can see that I have a function within a function. I have all that red stuff cubed. And again, like I promised, I will certainly allow you to see it. Okay? And so all that red stuff that I originally had as that blob of red there is going to be what my u is. So it's your inside piece of your function that you are, maybe it's inside of a trig function, or you are cubing it in this example. So that's my u. Now what I want you to find is not necessarily u prime, because u prime is another way of writing du, in this case with respect to x, so du dx. What I want you to write is just du, so it's kind of like multiplying both sides of that by dx. Or in other words, we're going to find the derivative of u, which is just du. And then over here, after I find the derivative of all this, I just took the derivative of x's. So the derivative of x squared is 2x with respect to x. So again, normally you probably would have said derivative of u with respect to x is 2x. All I'm asking you to do is multiply that dx to the other side, if you will, or think of it as all the u's on one side and all of the x's on the other. Okay? So that's my du. And then what I want you to start off substitution by, or this U-substitution, is by solving for dx. This is not something that we will do throughout all of the videos, but we are going to work on solving for dx. So I will divide both sides by 2x. And then when I look at my problem here, I'm going to do some substitution just as it calls for. Instead of dx, I'm going to put what dx is equal to. And instead of my u here, right, I'm going to put that u in place of x squared minus 9. So what my antiderivative will look like now is really u cubed. The 2x was just kind of hanging out. Notice I didn't highlight it green or blue because it was just a part of my original problem, just like the cubing was. And then the dx, which is really du over 2x. And if you have chosen the right function for u, you should notice that after a little bit of maybe algebraic manipulation, your new integrand, or what you're taking the antiderivative of, should look easier than your previous one. So for example, 2x divides by 2x and leaves a 1. So I'm really just anti-differentiating u cubed du. And that, I think, is much easier than what we started with because I know that is u to the fourth over 4 plus c. And then the only thing I have to do to finish my problem is recognize that I did not start with u's, I started with x's. So u is x squared minus 9. And so put your function that you assigned to be u back in your final answer. Okay, let's look at another one. All right, so what you're looking for to start all of these is where is your function that is inside of another function? And I hope you can see that all this stuff in here is inside of a squared. Now don't worry that all of that is in the denominator because I can always write it to a negative exponent and then I don't have to worry about that being in the denominator anymore. So I'm going to let u be 1 plus x cubed because that's inside of a squared function. So then we're going to find du. Remember, just du, not necessarily over or with respect to x here. We're doing it separately. So derivative of 1 with respect to x is 0, and derivative of x cubed would be 3x squared with respect to x. And again, just for beginnings here, I want you to solve for dx. Now, if you are Calc 1 and done, as we have said in class so many times, like you only need Calculus 1 and you don't need to go on, you can solve for dx the entire time and not worry about what we're going to show you later. Otherwise, you will want to work on an inside-outside technique for U-sub, which we'll show you in a little while here. So for right now, we'll still solve for dx. So I'm going to divide both sides by 3x squared. And I'm going to do some substitution now. I'm going to rewrite my original function or my original integrand here. But the dx is now going to be this du over 3x squared. And all of this 1 plus x cubed is now just going to be the u. So this should be antiderivative. X squared in my numerator is left alone. That was an aggressive denominator. I don't need it quite that big because now the denominator is only u squared, because that's what I let my u be, times dx. So du over 3x squared was what we found dx to be. And if you did this correct, not only is your integral going to be easier to determine than the original one, but you should also not have any x's left. And we'll talk later in this video series about what to do if you used U-substitution and you still have another variable other than u left in your integral. That's like the extra variable case, and we'll go through those examples later. So I see here x squared divided by x squared is 1. And I also see this 3 in the denominator. So I'm going to go ahead, that is a coefficient of my whole problem. So I'm going to write that in front of my integral. And then I'm going to write, I have du left in my numerator and u squared left in my denominator. So the other way to write that if I wanted to is u to the negative 2. Okay, which I know I can integrate. It's power rule. So I'm going to keep the 1/3. And then this is going to be u, if I add 1 to negative 2, I get negative 1. And divide by that negative 1. And if you're concerned with it looking like I'm subtracting, you can use parentheses. And so one way to rewrite this would be negative 1/3 times 1 over u. And my u that I assigned from the very beginning was 1 plus x cubed. So I can stop right here. Don't forget that plus c, that constant of integration, becomes so important throughout all of these. All right, so let's do another one here. And again, this becomes a question of, who should be your u. And I will tell you one thing, that if you make your u too complicated and you're having to use chain rule once you assign your u, so if I assign all of this, for example, to be my u, and I'm going through to find du, and I say, okay, bring down my exponent, keep your base the same, subtract 1, times the derivative of what's inside with respect to t, that's too much. I'm not saying that it doesn't work. I'm saying that there's probably a better or easier or maybe a little bit more efficient technique. And U-substitution should eliminate the need for most of your chain rules. So I'm just going to let that inside piece be our u, because I can always integrate u to a power. That's just my power rule. All right, so then du, derivative of 1 is 0, and derivative of 1 over t, if you need to think about this as t to the negative 1, you can, because this would be negative 1 over t squared, or negative 1 t to the negative 2. Again, don't forget that dt. Now, when we solve for dt here, right now, it's dt is being multiplied by negative 1 over t squared. So we're going to actually multiply both sides by negative t squared. So I have negative t squared du is equal to dt. And let's put this all in and see if my integral gets any better. So I have the antiderivative of 1 plus 1 over t, that's what I let be u, so I'll say u cubed. I'm just going to copy down the 1 over t squared here in the middle. That was my middle factor, basically. Just leave that there. And then exchange your dt. Well, dt I found to be a negative t squared du. So it is very important that you don't just turn dt into du. If that was the case and you're just doing an exchange, dt for du, then that meant in the beginning t must have been u, so why are you even using substitution? All you're doing is changing your variables. You're not really helping yourself out at all. So it's very important that you actually find the function that is represented by dt or dx or dm, whatever variable you have. And now I also think while we are going through this and figuring out what the more simplified integral is going to look like, I will bring out constant coefficients. So for example, that negative I'm going to bring out front. There's no other coefficient, but t squared divided by t squared is 1. So I'm just integrating u cubed times 1, which is u cubed du. And so this should be the opposite of u to the 4th over 4 plus c, and u is 1 plus 1 over t. So you can write this a couple different ways. I'm just going to write negative 1/4 as a coefficient of this, and it would be u to the 4th, which 1 plus 1 over t. It was off my screen, so I couldn't see what u was, but there we go. So negative 1/4, and that comes just from this negative here and that 4 right there. And then my u to the 4th, and u was 1 plus 1 over t. And that finishes that one. Let's look at another one. Okay, let's look at this next one here. This is asking us to take this differential equation, dy equals 4x dx plus 4x over the square root of 16 minus x squared dx. And it's asking us to solve for y. Well, if it gives us dy, hopefully we can see that we can integrate, and they even gave us individual terms here, all with respect to x. So I can integrate those individual terms, and I will have this solved for y. So hopefully we can see this first one, the antiderivative of 4x with respect to x would be 4, then it will become x squared over 2. So I know this first term here is 2x squared. Okay, I don't want to lose that though as we go through the rest of the problem. So the next part though is where this U substitution is going to be required, and hopefully you can see that I have a function within a function because I have 16 minus x squared, which is underneath this square root, okay, or to the 1/2 power in the denominator, or if you wanted to bring it up, it's to the negative 1/2 power in the numerator. So I'm going to let U be 16 minus x squared. And let's just get this to a point where we can integrate it, and then we can pause the video. You can try the integration and see how you're doing with that part. So if u is 16 minus x squared, du is then negative 2x dx, and hopefully that part is decently simple for you. Should be just power rule there. And then if we solve for dx, we're dividing both sides by negative 2x. Okay, make sure you don't add 2x to both sides. We're just dividing. And then let's rewrite what we have. Okay, so I'm not going to copy it twice. I'll just copy it here. I have 4x that I'm just going to copy down. So there's my 4x over square root of u. Now you can write square root of u, or you can write u to the 1/2. It depends on how you like seeing it. I think most people, as they're getting used to this, probably do write square root of u, so I'll keep it square root of u. And then times dx, and our dx is du over negative 2x. And again, if you're going to look at that negative as a subtraction, you definitely want to use parentheses to help you out. So what I'm going to do instead is say x divided by x is 1. 4 divided by negative 2 is negative 2. So I will put a negative 2 in front of this. And let's see from here, now that my integral is all in terms of u, let's see from here if you can finish it. So go ahead and pause it, finish the problem, get a really good equation for y, and then push play when you are done. All right, so let's take a look at it and see what you got. When we're here, don't forget your plus c at some point, even if you just put it at the end and put your answer, with that plus c, that's fine. That recognition is still there. The du over square root of u should be written as u to the negative 1/2, because then I can just power rule that. And what happens is when you add 1 to negative 1/2, you get positive 1/2, but instead of dividing by positive 1/2, I multiplied by 2. So that's why that becomes a minus 4, and u to the 1/2 is the same thing as square root of u, and my u was 16 minus x squared. So there's the equation we should have gotten. All right, so let's do one with trigonometry and then one with E, and we'll call it a day for this is just, again, the beginnings of U substitution, just sort of getting you started with this idea. So with trig, it's not always apparent. Here's my beginning integral. It's not always obvious. Sometimes you might think it is, sometimes you might not. Which trig function should be u. Now remember, you can write u to any power. So I don't necessarily want my u to include the exponent in this case. So let's just see what happens and see if we can come up with which one would be better. So if I let u be this secant of x part, then I could write that as u squared. But I want to see if the rest of this then is going to go away. So for example, if u is secant x, then du, well, the derivative of secant x is secant x tangent x dx. And that is going to give me problems because I want that to divide into that tangent to the 4th nice and even, and that doesn't look like that's going to happen. So just take a quick pause and try the other trig function. All right, so if u is tangent x, so now I'll erase these. If u is this tangent, I can write this as u to the 4th. And if u is tangent x, then du is secant squared x dx. and that matches this whole thing perfectly. So if I see that, if you can make that jump, then you can go right to, ooh, I know, I let tangent of x be u. This is going to be my winner here. I let tangent of x be u, so this first part is u to the fourth. And then this whole second factor here, if you will, or this whole rest of this integrand, secant squared x dx, is exactly matching what my du is. So I can do that replacement and just say that this is u to the fourth du. I don't necessarily have to go all the way and solve for dx every single time. You certainly could still do that. You're going to get the same answer. So if I integrate this, I get u to the fifth over 5. Don't forget your plus c, constant of integration, and put your u back in. So this would be tangent to the fifth x over 5 plus c. And I'll show you another one like that here with e. Now, there's more than one way, of course, to do a lot of these problems. I'm trying to keep it simple and also efficient so you can replicate this and have success no matter what the problem says. So one general rule is that we know how to integrate e to the u with respect to u. This is e to the u plus c. Okay? So if that's the case, I can see that I have a function, right, in place of where that exponent u normally is. So I'm going to let that exponent be my u. So negative x cubed is u. And then we got to find du. So du is negative 3x squared dx. Again, you can go all the way and solve for dx, or you can pause and take a step back and say, ooh, look at this. In my problem, I have negative 3x squared dx, and I'm saying that's exactly what du is. So if I do a rewrite here, I don't necessarily need to go all the way and solve for dx because I can see the substitution here. This is e to the u because I let negative x cubed be u. And then the rest of this green is my du. And we already said we know how to integrate that. It's e to the u plus c. And my u was negative x cubed. Certainly, if you go all the way and solve for dx, it works out the same. Let me just show you real quick here. Dx would be du over negative 3x squared. So when you rewrite this integral from the beginning, you have the antiderivative of e to the u times the negative 3x squared from the original times your dx, which you found to be du over negative 3x squared. Negative 3x squared divided by negative 3x squared is 1. And you're anti-differentiating e to the u du, and you're going to end up in the same place. I hope you found that helpful. Thanks for watching. More to come on U-Sub. Don't forget.